The main use of our Hadoop cluster is to store the information we have on all the internauts as they move around the internet, information on our clients, what sort of products they have to sell at what different prices, and it's also used to calculate the models that are used to participate in the real-time bidding for the ads. Okay, this button. So we're a team of not so many people, 7 people, and we work in Paris. Criteo has research offices in Paris, Palo Alto, which turns out well, and in Michigan. Back in 2014, which was soon after I joined the company, we had an Hadoop cluster of about 1,200 nodes. It was used to run 100,000 jobs a day, so these are jobs to import data into the cluster, because we have many sites all around the world which collect data from navigation as people use browse the internet. We put pixels on many different pages so we know where people go. We know what sort of products they buy. We never know who you are. We just know that this person went to this website, the same person went to the other website and bought some shoes on this website and went to this other website afterwards. So we never want to know who the people are. We just want to know what they do. So some of the jobs are to import that information as it arrives in our clusters. Some of the jobs are to generate the models that we use to participate in the bidding. And some of the other jobs are business intelligence, people who want to analyze the data to find what the trends are, what's happening, if there's any fraud. We have other jobs as well that do the billing. At that time we were using HP machines. And you can see the quantity of data was actually quite important. Even back in 2014, we were importing 40 terabytes a day. And it's very important because it's used to do the modding, to make the models, to do the billing, which is almost important, to send out the bills to our different clients at the end of the month, and to do the business analysis, because not only do we analyze what's happening, but our clients want to analyze how well their advertising programs are going. So as you may or may not know, Hadoop provides local redundancy. Who's used Hadoop? Who knows what I'm talking about when I say Hadoop? Some of you don't. Okay, all right, okay, let me go back a step. So Hadoop is a way of joining many cheap computers together to store data and to calculate on the data. So the idea is when one single machine fails, when 2 machines fail, it's not a problem because you have 3 copies of the data. If you lose a whole rack, it's not a problem because every block is on at least two different racks. The Hadoop cluster is run by what are called name nodes, so they do the mapping between file names. So they contain the hierarchy of file names, like a Linux file system. They contain the mapping between the hierarchy of file names and where the blocks actually are. So the name node knows all the files, and it knows where the 3 copies of every block are. So they're critical. And we have a resource manager that's responsible for running the different jobs. So it knows... People send a job and say, okay, when you run a job, the job knows, and the resource manager knows which data it's going to need to run the job. And so it will split the job up into many subtasks, if you like, and it will try and position them as close to the data that they're going to want to read as possible. Okay? So in our system, we had 1,200 machines, 100,000 jobs a day, so the resource manager would say, okay, this job needs to read these files, and the name node knows where the blocks of these files are, and the resource manager will split the job up into many small jobs and run them on the same node, or at least on the same rack where the blocks of the files are. As you can see from the photo, each block is stored 3 times. On 2 different racks, and we have we have a certain amount of redundancy provided by Hadoop itself. Okay, but Oops, going the wrong way. But what we don't... infrastructure provides another level of redundancy. We have multiple routers on the top of the rack because, of course, all these 1,200 machines are connected together. But in our new system, sometimes we still have a single top of rack switch. So if we lose the top of rack switch, we lose the rack. We have multiple power sources coming into our data centers, but we only have a single power supply per rack. So there are many things we're not protected against. We're not protected if the data center catches on fire. If we have 3 or more data nodes that fail at the same time, as soon as a data node is seen as failed by the name node will recopy the blocks that have just been lost, that are now only replicated twice, and will copy them onto a third node. But if you lose 3 nodes within sort of 15 minutes, then you lose blocks because the name node hasn't had time to make new copies of the blocks that have just been lost. We're not protected if we lose 2 racks in the same day because it takes quite a long time to replicate the data from a whole rack onto another rack. And we're not protected if an operator, DevOps, makes a mistake. I'm not sure how clear this is for people that haven't used Hadoop before. So this is redundancy provided by the system, but only up to a certain level. So the question is, what do we do if we have bigger failures? We thought about backing up our 30 petabytes of data in the cloud, but that just takes so long because we're now importing, so now a few years later we're importing 100 terabytes a day, and we're actually creating extra 80 terabytes. And so the fastest link we could get to something like Amazon in the cloud was at 50 gigabits a second, and it just takes too long to back up. And if we did lose all our data and wanted to start working again, the very minimum we would need to restore would be 2 petabytes. And it just takes too long to pull that information back out of the cloud. And of course, we need the compute because these nodes have storage and compute. And so if we lose the data center, not only do we lose our petabytes of data, but we also lose the thousands of CPU of compute. We worked out what would cost to do the compute in the cloud. We'd have to reserve 20,000 CPUs, which costs a lot of money. And working in the cloud is very useful when you have some sort of elasticity in your compute demand. Sometimes you compute a lot, a bit later you compute less, but we don't have that. Our data centers run at 100% most of the time. So there are no spare resources to return, to stop paying for at any time of the day. The other factor we had in mind was that we already have data centers. We have data centers all around the world. So the Hadoop cluster at the moment is getting up to 3,000 machines, but Hadoop has got over 20,000 machines. So we're only about 10% of Critio's mass. So Critio already has lots of data centers. We know how to make data centers so that our finance people told us that calculating in the cloud would cost us calculating and storing in the cloud would cost us 8 times more. So what did that mean? So, like I said, we had this data center. It wasn't redundant. We needed to build a new data center. So we made a new data center. It's big enough for 5,000 machines. It was delivered a bit over a year ago. We have a non-blocking network, or we had a non-blocking network, which meant that any node could transmit at full speed without being slowed down by the network. So every machine had 10 gigabit per second endpoints. We had level 3 routing rather than level 2 routing. We have a cross topology, which means you have spines and super spines, which allows any node to talk to any other node at full speed without being overloaded, without being slowed down by the network. We currently have 1 megawatt coming into the data center, but we can double that. What's important to know here that we didn't know that it was impossible to do this in 9 months, but we did it, more or less. So where are we at now? So what we did was, up until then, we'd always use HP machines. But HP was getting more and more expensive because they knew that we always bought HP machines, so they had no reason to make an effort on the prices. So this time we did a call for tenders. We got 3 replies. HP was one of them and 2 other companies. They each provided very similar machines. 2 of them had 16 disks and the other only had 12. Same CPU, same amount of memory. There's only sort of one network card out there that does what we need it to. But we did have 2 different RAID cards, which will become important a bit later. So we made 3 10-node clusters. We wanted to test the disk bandwidth, the network bandwidth that we got out of these machines. So we ran some TeraGen. So people who do Hadoop know that this is a fairly standard test program where you generate data. So we generated terabytes of data. We did it twice or many times. Once with 0 replication, where we just wanted to pump out as much data as possible onto the local disk. So as I explained before, jobs read data on the machine they're running on. Of course, they tend to create data on the machine they're running on. So when you have 0 replication, you just pump out as much data as possible on the local disks. We also ran the test with a higher replication factor, which would then test the network, because the job would create a copy of the block on the local machine and then send over the network the blocks to other machines. And a terasort is when you sort terabytes of data. So we ran these tests, and what we found is that they were more or less they're almost the same. So one of the constructors managed to provide us with 4 dead on arrival disks, so that was a negative point, and more of their disks failed, and they used 20% more power than the other constructors, so we eliminated that constructor. And then the remaining 2 was our historic constructor HP and a cheaper one, Huawei. So we bought some Huawei machines with this LSI 3008 RAID card. And so the situation we have now is that before we used to have one type of hardware. So now we need to deal with different configuration depending on machine. They don't have the same number of disks. They don't have the same amount of memory. Some of our clusters have both types of hardware clusters, so we need to deal with that as well. But the advantage is that at each order we can play the different constructors off amongst themselves and insist that we get the best prices for the hardware we want. And we're trying also to move to a model where each time we order new machines, we can choose that CPU, this motherboard, these disks, this RAID card, this network card, and mix them together ourselves, with the aim of avoiding vendor lock-in, so that at each order we can choose the cheapest and the best option. So after a while, we had a new data center with at the beginning about 750 machines in it. So we configured it using Chef. I don't know if you know what Chef is. Chef is a way to automatically configure machines. There's an agent that runs on the machine that pulls the configuration from a central server and sets up the machine automatically. So it means that the infrastructure, how the network's configured, what packages are installed, how the network's configured, how the machine is configured, how Hadoop is configured, all that is in this Ruby code that's stored in Git. So all that's automated so that we can just switch a rack of machines on and they configure themselves automatically. So we had our new cluster. We started testing it. We tested it with sorts of petabytes of data that would run for 10 hours on 700 machines. We'd tune Hadoop so it would run well at this scale, because not that many Hadoop clusters are this big. And of course we had problems. The name node, which is this main machine which contains the mapping between the file names and the blocks, would crash. We found there was a kernel bug in the version of the Linux kernel we were using, so we needed to upgrade all the machines. But we wanted to do this without stopping the service. So we learned that what you need to do is you need to restart the machines rack by rack. At the beginning, we restarted the machines node by node, but that had the disadvantage that jobs would run, the node would be killed, and so the sub-jobs or the tasks would be running on that node would be killed and they'd be restarted. But some of them would be restarted on the node that you're about to kill the next time, and so certain jobs would just never finish because we'd keep killing the machines that the jobs are running on. If you do a rack by rack, by the time you've restarted a rack, most jobs are finished, so the tasks of a job are only killed once. something we learnt along the way. So this is a photo of our new data center in the outskirts of Paris in France. And so it's just rows and rows of machine with a central corridor which is cold because we pump cold air in. The cold air goes through the machines, and behind the machines there's the hot corridor where all the hot air goes out. We made a couple of mistakes, which probably means more to people that have made Hadoop clusters. We decided in the beginning that we'd just buy one sort of machine that we'd use both for the name node and for the data nodes, with the idea that if a name node crashes, well, we just steal a data node and move the name node service onto the data node. That sounds easy, but if you were using Kerberos for the login for the security on a cluster, and moving Kerberos principles from machine to machine is quite difficult. And it turned out the machines we bought with 256 gigabytes of memory are just not big enough for a name node of a cluster of this size. So we had to buy new, bigger machines, which I'll talk about a bit later. And we also decided that it wasn't up to us to run DNS and Kerberos services, so we gave them away to other teams. The other mistake was we chose the wrong RAID controller. What happened was that this would just randomly vanish. There'd be no diagnostics, it would just be invisible, there'd be no LED on the back of the machine. I tried to, so we lost hundreds of disks like this. And so what I did was I said, okay, I can no longer see the disk, so I turned on the identity LED on the other disks, and I went out myself to the data center and spent a whole day pulling disks out and pushing them back in again, because it turned out that the disks were actually okay, there's just some transient error, and you need to power cycle the disk to get them to work again. So the only way to do that is to power cycle the machine or to pull the disks out and push them back in. So this is one of the advantages of working for a company that has their own data centers. You can actually touch the machines if that's what you want to do. So we decided we didn't want this RAID card anymore. So we've now got 700 machines on a cluster, which is now about 1,200 machines on this new cluster. And we need to change the RAID cards. So we did this rack by rack. We'd decommission a rack, which means we tell the name node that we're going to switch the rack off. It makes a third copy of all the blocks that are on this rack on other racks, and then we switch it off. The machines come back because they've got a new RAID card, without any blocks. And then the name node would gradually fill the machines back again. This turned out to be a lot harder than that, and we had lots and lots of stability problems. So we finally finished that just 2 weeks ago. It took about 3 months. It's a big effort to do 700 interventions on 700 machines on a running cluster. Going back in time a bit before we've changed the RAID cards. So we've now got a new cluster which is online. And this was good because we had two clusters. We have the old one, which is still running, and the new one. The users love it because we have huge amounts of resources. So they found new and wonderful things to do with the data. So unfortunately, that meant that they were now using more capacity than the new cluster could provide. So we could no longer switch the old one off because the idea was to have just one cluster running. Well, the idea was to move everything to the new cluster, switch the old one up and upgrade it. But now we're in the situation where it was impossible to stop the old cluster because the users were using both of them. So now we had a wonderful situation in that previously we had two critical clusters. If we lost it, Criteo would be in a very bad state. Now we have two critical clusters. And what's worse is that the old one is running an old version of Hadoop and the new one's running a more recent version. And so our team, which hasn't suddenly doubled in size, now has to deal with two different types of hardware and two different Hadoop versions, and both of them are critical to the company. So what was the solution? Well, the solution was to throw money at the problem. We bought hundreds of new machines. So today the new cluster has got almost 1,400 machines. We're adding another 650 in the next, we'll be at 3,000 data nodes by the end of the year. So this will give us enough capacity to move all the jobs onto the new cluster. But we're a bit worried that our name node is going to be a little bit too small. So this is what I just said. We're going to move all the jobs and the data to the new one and stop the old one. Things are not, yes. But this is still not enough, because the new cluster is now much bigger than the old cluster. The old cluster had 1,200 machines, but they're much smaller machines. The new cluster will have 3,000 machines at the end of the year. So we still need some redundancy. So we're going to build another cluster, which will be about the same size as the new one, so somewhere between 2,000 and 3,000 machines. It will be mainly used for development, machine learning. The machine learning is when we create the models that are used to participate in the online auctions. And it's also going to be used for development and business intelligence uses. It will have all the data that's needed for the service jobs that are running on the main cluster. So that if we lose the main cluster, we'll be able to switch all the service jobs to the newer cluster, which we're going to build next year. And of course, the human users will be kicked off for the time being. Okay, so that's the plan for next year. So we're going to do the same thing. We're going to do another round of tenders, except this time we've decided we need more CPU. I guess that really means more CPU per rack. So we want to increase the ratio of CPU to disk space. So we found some denser machines. We've got some 4U machines. Does that mean anything to anybody? You have racks, and racks have got 20 slots in them. So each slot's a unit. So we've got some 4-unit machines, which have each got 8 computers in them. And you can see how much disk space they have. So they've got 16 CPUs. Or we've got some 2U machines, which have got the same number of CPUs per rack space, but have got a little bit more disk space. So the task for the next coming months is to validate that these new machines work well, and then we'll buy a couple of racks of each type of machine and then test them. So here's a photo of these machines. So these are the 4U machines with you can see the 8 nodes, and these are the 2U machines. You can see the 4 nodes. So here's some of the disks are at the front. Here the disks are at the back. So these are the new machines that are just coming on the market now. And we'll test them and buy some of them at the end of the year and make our new cluster. So, like I said at the beginning, there's just still 7 of us, and we're heading up towards... So at the moment we're ramping up to 3,000 machines in the new cluster. The old cluster's still not off yet, so we've still got about 4,000 machines, and we're going to be building a new cluster next year. So the important thing here is everything has to be automated. When you change a disk, you can't have somebody by hand saying, okay, we've moved the disk and we'll soon be having a new disk. I'm not sure how much time I have left, because something's written in Polish in front of some sort of warning message has come up. Okay, saying you need to... Okay, all right. So the important thing here is when you're running on this scale and when you're not somewhere where labour is cheap, is that you need to automate everything. You need to automate changing disks, because, well, I'll let you do the calculations of how many disks we've got, but it's well over 30,000. They fail all the time. We need to have... The LED on the disk needs to come on when it fails, and somebody needs to go and change it, and it all needs to happen automatically. When we're adding racks of new machines, we can't go and look at each machine by hand. They just need to be delivered working. We need to switch them on. Chef needs to do its magic, and they just need to come online. So all this means that all our configuration, network, everything I mentioned before, everything is seen as code, so it's tested. We use Kitchen. Kitchen is the way you test chef recipes, of course, obviously. Chef Specs, which runs a virtual machine. It will configure the virtual machine, and then you can test certain properties of it, which is a way to test your recipes, which are the rules that are used on the nodes work, and that you don't break something, you don't break an old function when you increase a new one. So all the changes to our infrastructure are done by merge requests with reviews. We're now starting to use another technique when we need to to restart all the nodes. Instead of doing it, we're now being able to do that when you want to restart the data node service, for example. That can be done node by node. And you don't want to do that by hand. You don't want to restart 3,000 machines by hand. So we're now running, the nodes actually now talk amongst themselves. Say, okay, I need to restart. Is the cluster in a state where it can be restarted without any risk? So this is a lot of work that really is code. We're writing Ruby code. We're writing tests in Ruby code. We're doing merge requests. People discuss the code, how it looks. Is it good? Is it maintainable? Are the tests complete? And so even though it looks like just a pure infrastructure job, it's becoming more and more a programming job. We also have our own, so we have clusters for the users. But we also have our own cluster where we can test changes, a new version of Hadoop, our new chef recipes to see that they don't break the cluster. There are many bugs where we find some bugs in Hadoop, and we use our lake cluster to test them as well. So this is a cluster of 50 or 60 machines, which is reserved for us playing with things, just so we haven't broken anything, and to do some minor tests of performance. But testing of performance, it's not at all at the same scale as production clusters. So unfortunately, some testing really does happen in production. And we also have, this is a photo of the lab we use to do hardware tests, where we have the old HP machines that we still have. They're the new YY machines we have, and they're the two machines you saw a little earlier that we're thinking about buying for the new data center next year. So there's a lot of hardware testing and a lot of code to configure the hardware. So to keep all this thing running, we need to tune Hadoop, because a lot of people have Hadoop clusters of 100 machines or 500 machines, but when you start moving up to 3,000 machines, you need to have a GVM with, well, as you can see, over 300 gigabytes of heap. So that takes a lot of work to keep the garbage collection under control. We spent a lot of time tuning the garbage collection on the name node. We tested the serial garbage collector, which wasn't very efficient with our CPUs, which were reasonably quick but mainly had lots and lots of threads. The parallel one wasn't good either. We tested the concurrent mark sweep as well, which was good because it gave short pauses, but the throughput wasn't enough, so the name node would never catch up. At the moment, we're using the G1 garbage collector, which is working well. We thought about testing the Azul GVM, which is an alternative GVM, which is guaranteed to be pauseless, so there are never stop-the-world garbage collections. But for the moment, we're surviving on our machine with 512 gigabytes of memory, and the heap size you see, it's good enough for our cluster at the moment of 1,300 nodes, and we'll see what happens as we move towards the end of the year and 3,000 nodes. We find bugs. We find bugs in Hadoop. Some of them have already been fixed, but are not fixed in the version of Hadoop we're using. So that means that we spend quite a bit of time investigating what the problem is, trying to find the appropriate bug fix, backporting it to the version of Hadoop we use. And so these are some of the fixes that we've invented ourselves, and other ones that we've backported to the version of Hadoop that we're using. And the next thing we're going to have to do to keep on top of things is we're going to have to try and upgrade the version of Hadoop we're using, which is difficult because we've got a cluster that's critical to the company. We can't stop it because it needs to run all the time, and so we have to try and convince the management to allow us to upgrade the cluster in place, which makes everybody very, very nervous. The other thing you need to do when you have a cluster of that size is you need to do lots and lots of monitoring. You need to keep an eye on the name node. You need to make sure that it's not missing any blocks, because as data nodes fail, they might take blocks with them, and if unfortunately the other data nodes with the same blocks have failed at the same time or have a problem, the name node might miss a block. The data nodes send block reports to the name node, and sometimes they're lost as well, so we need to keep an eye that the name node's not missing blocks. We need to keep an eye on how long the garbage collection takes. Name nodes do something called checkpointing, where they dump an image of their database of the mapping between file names and blocks to disk. We need to make sure that happens, because if it doesn't and your name node crashes, it's very hard to start it again. We need to check the number of operations per second is reasonable. If any of these graphs move out of the nominal range, it means we need to be woken up in the middle of the night to work out what's going on. We need to keep an eye on the data nodes. We need to check that the disks are still working. We need to check that the read and write throughputs remains the same and that we haven't filled the disks up. Yarn, so if this is the storage part. Yarn is the part that runs the jobs. So we need to check that jobs don't spend too long in the queue waiting to be run. We need to check that jobs suddenly don't start using more CPU time, that there's extra CPU for new jobs. We need to check that the resource manager doesn't have too many operations, that there aren't bad nodes that are failing jobs. And so we've written lots and lots of probes which emulate user jobs that are run every minute. And we write graphs of how long it takes to run standard operations which don't change. And if it suddenly takes longer to create a file, to create a directory, to read a file, then we know something's going on. Zookeepers are a service that it's a shared consistent cache. So we have Zookeeper clusters of 5 or 3 nodes which are used internally or by the users. So we need to check that they're in a good condition, because when they fail, the cluster comes to a grinding halt. So that's a lot of monitoring. So this gives our standard way of working, where we've always got monitoring in front of our eyes as we keep an eye on what's happening and check that everything's under control. So more and more, so this is raw data, I guess, and now we're starting to write probes, second level probes, which analyze this data and say, okay, the value is it's not just that the value is too high now, it's the value is changing too fast. And so it's an ongoing process to understand what you need to monitor and then how you need to monitor it. And then when you need to be alerted, you need to be woken up in the middle of the night, or it can be something that can be dealt with during the next working day. As I said, the name nodes, they're critical, otherwise nothing works. We found that the name node was a lot of Java code which does a lot of sequential operations, some operations keep locks for a long time. So a failover is when a name node dies and the other one needs to become the master name node. They were taking too long. The heartbeats from the data nodes, where the data nodes send the list of the blocks they have, were being lost because the name node couldn't deal with them fast enough. So we needed a faster CPU. So we upgraded our CPU to some of the fastest machines we could find with lots of memory. So that's working well at the moment with 1,300 nodes, and we'll see what happens at the end of the year. And do we need to start looking for terabytes of memory or even faster machines? So this is one of the other problems we had. So in the original cluster, we were using a RAID controller made by HP, which we thought, because this was the only one we'd ever used, we thought this was just how RAID controllers worked. So we use RAID 0 because HDFS Hadoop provides redundancy at an internode level, not on disk by disk on the same machine. So what we had with this RAID card is the status of the disk seen by the operating system would almost always match the status of the disk as seen by the RAID card. So if a disk fails, the OS and the RAID card would both agree that the disk has failed at about the same time. And then the RAID card would block any access to the disk. This is very good because the RAID card, because it's hardware, it's able to switch the LED on at the back of the machine showing which disk has failed. And our infrastructure team monitors the state of the disk using out of band via the maintenance network of each machine, because each machine has got the main network and the lower speed maintenance network. So that they can keep out of our way and do things independently, they monitor the disk by the out of band interface. So this was good. Everything worked well. A disk would fail. The OS and Hadoop and HDFS would see the disk is failed, and so would stop using it. The LED would switch on, and so somebody would come past and change the disks. And we just assumed that this is the way RAID controllers worked. But of course, unfortunately, we found out that's not the case, because when we bought a different RAID controller, which we thought would be just as good, it had a different threshold. So it's much more reluctant to say that a disk is dead. So now we have the situation where the operating system has had read errors or write errors on the disk, but the RAID controller still thinks that the disk is good. So this means that we're getting timeouts because the OS and the services running on the machine are trying to access a disk that has errors. There's no error for the out-of-band monitoring to see, so we're not getting alerts saying that the disk should be changed. There's no LED on the back of the machine to say that the disk is dead, so the maintenance people can come past and change the right disk. And so this is a new major problem which we're now, went the wrong way, which we're now trying to deal with. So the one solution is obvious, is to just buy the RAID controller that we're used to using. The problem is the constructor knows that their RAID controller provides extra value, so they will only sell it to us in an entire machine. So that's vendor lock-in for you. We could create a team which could try and analyse all the different ways a disk can fail, as seen by the operating system. And when it decides that a disk has failed, it would need to stop the usage of the disk. It would need to try and perhaps format the disk to see it could be made to work again, but you only want to do that once, so it needs some history. When it's decided the disk is failed, it needs to open a ticket so the disk can be changed. It somehow needs to switch on an identification LED, but this is a lot of work that we're not big enough. So we discussed with the constructor how other companies like in China do that, with even bigger clusters, and they just have lots and lots of people that deal with this situation. So this would cost us lots of money and give us vendor lock-in. This is a lot of work for us that we're not really set up to do. And so the other solution is to try and get the vendor to solve the problem, which we're discussing with the constructor now. But that means they're going to develop. They don't own the RAID card. They can just provide code that runs on the RAID card but not in the RAID card firmware. So they say they're going to develop that for us, and then we get to test and debug it on our production machines. And then once again, we've got vendor lock-in. So this is mainly just an example to show that you can say, okay, we're just going to change RAID cards. And it turns out to be a real problem when you're running at the scale we have, because when you've got 40 or 50,000 disks, you just can't afford to get it wrong and to change the disk at the wrong time or to reformat the wrong disk. And you just don't have enough time to deal with all these problems by hand. So this is one of the current problems that we're working on at the moment. How are we going to deal with this new RAID card? Other things we've learned along the way is that if you start off with a small cluster, things that just work on a small scale suddenly stop working when you start adding machines. Some of the very simple ones were that every time we installed a new machine, we just downloaded all the packages from the internet, which sort of works when you have 100 machines, but when you've got thousands of machines that all want to download at the same time, companies start to see that you're downloading thousands of copies of the same package, and they blacklist you and your cluster stops working. We also had an idea when the cluster was smaller that we'd use the DNS as a database to share information between the data node and the rack. For example, the data node needs to, in some persistent way, indicate what rack it's in, and we decided to put a text record in the DNS to do that. And once again, it's something that works when you have 10, 100 machines, even 500 machines. But when you start getting up into 1,000 machines, you need to redo it. So the advice is to think about at the very beginning, okay, this seems to work on 10 machines. Will it work on 1,000 machines? And if it won't, then just don't do it. We have many adventures happen. The graph in the background shows a user that decided to create 20 million files and 20 petabytes of data on a Friday afternoon. It was a bit unfortunate it was Friday afternoon. As we were leaving, we sort of felt that something was going wrong, but things were still working more or less. And then sometime during Friday night, the name node just got stuck because with an extra 20 petabytes of data, it just spent all its time doing garbage collections. We realized that it didn't have enough memory, so we increased the heap of the standby to 85% of the RAM and we restarted it. But the restart failed because we just had too many blocks, so the failover, and then when we tried to fail, when we finally did get it working, the failover crashed. So the cluster just stopped working completely. The FS image, which is an image of the number of the blocks and the mapping, was corrupted on one of the name nodes, and because it was the transfer that's meant to happen automatically, it stopped happening because of the size had gotten too big. So we spent all weekend working on this. We ended up having to hand choose the edits, the modifications to the file system by hand. We managed to restart one of the name nodes by increasing the heap size to the maximum possible on the machine. And then we isolated that. We did that by isolating it from the data nodes, because 1,200 data nodes all sending information to the name node at the same time as it was trying to rebuild its data structures just killed it. So we used IP tables to isolate the name node from its data node. And once the name node was stable, we started to reconnect the data nodes rack by rack to the data node. So we spent the whole weekend fixing that. The lessons to be learnt, I guess, are slightly better monitoring so that we know sort of after when a user has created 5 million files, we get alerted rather than when the cluster dies at 20 million files. And we learnt that we need a bit more monitoring so that we know when FS images are starting to get corrupt. And we learnt that we needed a bigger name node. So you can see the graph of what one of the users did to us Friday afternoon. So this was actually an intern which had just came in to work for the company. I think he'd been there for about a week, and he ran a job on the production cluster using the production quota because that's what people said that everybody does, and he got it slightly wrong and he created 20 million files. We have other problems that happen every now and then. The resource manager, which is the, as I said, the component that schedules jobs, suddenly stops running. We find we get woken up in the middle of the night because we're only using 8% of the cluster. And so there's some unknown bug where you have to fix it by hand. You have to kill certain applications. So this is another task we have, which is very, very different from the other infrastructure class. We have to debug thousands of lines of data of Java code to try and find where the bug is that in certain situations causes the cluster to slow down. So as we provide this essential service, we need to decide what we're actually providing. So one of the big tasks was to negotiate with our internal clients of what we're promising to do, how long it takes to do different HDFS file system operations, how long jobs should take to run, and how long we can take to handle requests to create new users, to fix problems, etc., etc. So we've had to add a lot of monitoring. We've had to try and learn to respect the service level agreements. And some of the services that we provide, we've decided are just best effort. And if they work, that's good, but you can't rely on them. So as I mentioned in the beginning, the aim was to have redundancy. We're not there yet. We're not even nearly there. Soon, next year, we'll be building a new data center, so we'll have 2 clusters. But we still have this other problem, which is that These clusters, infrastructure is code, so all the code that looks after the infrastructure, that keeps the network running, that formats the disks, that installs everything, is the same code. And it's stored on the same Chef server that's distributed by the same machine. So we need to be very careful that a single mistake in the code will not be immediately applied to both data centers and erase all the data in one fell swoop, as our friend says on Twitter, to make errors human, to propagate error to all services automatically, DevOps. So today, a quick summary of where we are. We have 2 production clusters. Soon we'll only have 1, and then next year we'll add the new one. Since these production clusters are running 2 different versions of Hadoop, we have 2 pre-prod clusters, 1 for each version. We have our lake infrastructure cluster where we do our tests. So you can see we've got 2 running the old version, 3 running the new. We've got, we're heading towards 3,000 data nodes. We have 50,000 cores. Lots and lots of disk space, lots and lots of RAM. Huge numbers of jobs that run all the time, 24 hours a day, which is one of the reasons that it's better not to use the cloud. And we churn through petabytes of data a day. So what are we going to be doing in the next little while? We're going to be continuing to optimize and fix bugs that we find in Hadoop, optimize how it's tuned, and find the bugs and fix them. We're adding hundreds of data nodes a month. We're going to build a brand new data center somewhere in Paris or near Amsterdam. We don't know yet. We need to once we have the second cluster running, we need to make them to work together. We need to copy petabytes of data between them every day. We need to improve the scheduling because we have so many jobs with different priority levels, with different requirements, that we need to rework the scheduling that we're currently using. Obviously, because of all this work we're hiring. So if you'd like to come and work for us, we have Criteo is about 2,600 people at the moment. About 800 of them work in what we call R&D, which means writing programs, running machines, setting up data centers. And the R&D centers are in Paris, in Palo Alto, and in Ann Arbor near Detroit in Michigan. So if you'd like to come and work for us, come and talk to me, send me an email, look me up on Twitter, or look at Criteo's website.